Okay, so let's go over the free fall problems you had from last night, starting with number 8, I believe. So number 8 is Kyle flying a helicopter when he drops a bag. When the bag falls for 2 seconds, what is its velocity and how far has it fallen? Okay, so we have dropped, which means VI is 0. It means A is 9.81 meters per second squared. So back this up so I can reach my paper better. And it says that it falls for 2 seconds. So delta t is 2 seconds. So part A, we want VF, and so we would use A equals VF minus VI over delta t. The VI is 0, so it'll just be VF equals A delta t. This A, of course, is down because it's gravity, but I don't actually need to put a negative in because everything's going down. So I get 9.81 meters per second squared times 2 seconds. So my VF ends up equaling 19.62 meters per second, and that's down. Part B wants to know what distance did it fall in that time, how far. So delta D. So if I have VI, A, and delta T, then I can use VI delta T plus 1/2 A delta T squared. Again, VI is 0, so this whole term disappears. Delta D is equal to 1/2 9.81 meters per second squared, 2 seconds squared. 2 squared is 4, half of 4 is 2. 2 times 9.81 is 19.62 meters this time down. So they look similar, and that's because of the 2 seconds, because 2 squared is 4, and you take half of it's 2 again. This guy, though, has units of meters per second in part A, and in part B it's a delta D, so it has units of meters. Number 9 is still Kyle, still flying in the same helicopter, but this time the helicopter is rising 5 meters per second. So the initial velocity is 5 meters per second up. For the bag that's being dropped, the acceleration will be 9.81 meters per second squared down. So right away we can see that we're going to need to use a negative for our acceleration this time because there's 2 opposing directions. Time is still 2 seconds, and the question wants to know what's the bag's velocity at the end of the 2 seconds. So again, A is equal to VF minus VI over delta t, but this time the VI doesn't go to 0. So we rearrange A delta t is equal to VF minus VI, so VF will equal VI plus A delta t. So VI is 5 meters per second up, so it goes in as positive. A is 9.81 meters per second squared down, so it has to go in as a negative. And so that's negative 19.62 and positive 5 meters per second. And so you end up getting a VF of negative 14.62 meters per second, where the negative means down. Okay, that's part A. Part B, again, wants how far the ball is, is it a ball or a bag? How far the bag has fallen. So delta D is equal to VI delta T 1/2 A delta T squared. So delta D is equal to positive 5 meters per second times 2 seconds plus 1/2 negative 9.81 meters per second squared, 2 seconds squared. So the first term is going to be positive 10 meters, and the second term is going to be negative 19.62 meters. So in the end, the bag has fallen negative 9.62 meters, again, where the negative means down. Part C wants to know how far below the helicopter is the bag. Okay, so now like the helicopter was going up and the bag was going down. So by the time the bag gets down here somewhere, 9.62 meters, the helicopter has gone up some amount. And so it wants to know what's the distance between the helicopter and the bag at the end of the 2 seconds. So to figure that out, we have to figure out how far up did the helicopter go. And we can do that because the helicopter, it told us, was moving at 5 meters per second. So we can do VAV equals delta D over delta T. So delta D of the helicopter is just VAV delta T. So it was going 5 meters per second for 2 seconds. So while the bag was falling, the helicopter was rising 10 meters. So the distance here is 10 meters, and here it's 9.62 meters. How far apart are they? It should be 19.62 meters, because one went up 10, the other went down 9.6. Okay? Number 10. Kyle's helicopter is now descending at 5 meters per second. So now we have VI is 5 meters per second down. A is still 9.81 meters per second down, and the time is still 2 seconds. And part A still wants final velocity. So A is equal to VF minus VI over delta T. So VF again multiplied by delta T, bring the VI over, VI plus A delta T. This time everything's down, so I don't actually have to put negatives in, or if I do, I put them in on both the VI and the A. So maybe just for fun I'll do that this time. So negative 5 meters per second, negative 9.81 meters per second squared, 2 seconds. And so negative 5 meters per second and negative 19.62 meters per second. So I get a VF going down of 24.62 meters per second. Works out to be negative, but that just means down. If I had called down positive, this would have been positive, this would have been positive, my answer would have worked out to be positive, and I would have said, oh, it's down because I called down positive. Okay, part B, same as before, wants to know how far did the bag fall. So delta D is equal to VI delta T, 1/2 A delta T squared. So delta D is equal to, maybe I'll switch back to positives now. I just wanted to show you, so just so as not to confuse you. Okay, so 5 meters per second, 2 seconds, 1/2 9.81 meters per second squared, 2 seconds squared. So delta D for the bag this time, 10 meters plus 19.62 meters. Delta D of the bag is 29.62 meters. Because it works out to be positive and I called positive down, it's down. Part C wants to know how far below the helicopter is the bag. So we have to do the same thing we did up there, and we have to find out how far did the helicopter move in that time. And so just like up there, we had VAV is equal to delta D over delta T. So this time, delta D is equal to VAV delta T again. And so delta D is equal to 5 meters per second going down times 2 seconds. Delta D is equal to 10 meters, but it's down this time. So this time, the helicopter, when the bag started to fall, so did the helicopter. So the bag went down 29.62 meters, but the helicopter went down 10. So how far are they apart? This time, it would be 19.62 meters would be the difference between them because they were both going down. Okay, so the distance between them. So notice in all 3 questions that the